Hey everyone, welcome back to my channel. I'm really excited to have you here today because we're going to dive deep into an intriguing topic. In this video, we'll be exploring how to build a neural network model to classify images of fire and non-fire scenes, which can have practical applications in fire detection and prevention systems. Throughout this video, I'll walk you through the entire process, from setting up the environment, importing the necessary libraries, and preparing the dataset, to creating and training the neural network model using Keras Inception, a powerful pre-trained deep learning model. Along the way, I'll also provide detailed explanations of the code and various techniques we'll use to pre-process the images and extract meaningful features. By the end of this video, you'll have a solid understanding of how to implement an image classification model using deep learning, and you'll be equipped with the knowledge to tackle similar problems in the future. So, if you're ready to learn and have some fun, let's get started. And, as always, if you find this video helpful, don't forget to hit the like button and subscribe to the channel for more awesome content. If you want to download the source code, then check the link in description. I have an article explaining everything along with all the code snippets, and I won't be speaking while I write code, so you can follow along with me. Now let's get started with import. This code is a Python script that imports various libraries and sets up the environment for image classification using Keras Deep Learning Library and scikit-learn for the training, evaluation, and optimization of a machine learning model. Let's go through the code step by step. Import libraries. Datetime is DT for working with dates and times. NumPy is NP for numerical operations and array manipulation. Pandas is PD for data manipulation and analysis. Matplotlib.pyplot is PLT and Seaborn is SNS for data visualization. OS for interacting with the operating system. Several modules from Keras.applications and Keras.preprocessing for loading pre-trained deep learning models and pre-processing images. MPL_toolkits.axes_grid1.imagegrid for creating a grid of images. Several modules from sklearn for logistic regression, model evaluation, and hyperparameter optimization. CV2, OpenCV library for image processing. sippy.stats.uniform for generating continuous random variables, tqdm for displaying progress bars, glob for finding file paths matching a pattern. Set up the plot styles. Use the 538 style for matplotlib plots. Set the white grid style for seaborn plots. Import more Keras modules for building and training a deep learning model. Model and sequential for creating Keras models. Several Keras layers for building the neural network architecture. NP_utils and to_categorical for working with categorical data. Configure the IPython interactive shell to display all the output of a cell. Interactive shell.ast_node_interactivity equals all. This code sets up the environment for a machine learning project, particularly for image classification tasks. The actual implementation of data loading, model creation, training, and evaluation is not present in this code snippet. You would need to add those parts to complete the project. This code snippet is responsible for setting up the cache directory to store pre-trained Keras models, specifically the Seption model, for later use in the project. Here's a step-by-step explanation. Define the cache_dir variable, which refers to the .keras directory in the user's home folder. The os.path.expand user function is used to get the path to the user's home folder, and os.path.join combines it with the .keras folder name. Check if the cache_dir exists. If it does not exist, create the directory using os.makedirs. Define the models_dir variable, which refers to the models subdirectory inside the .keras folder. Again, os.path.join is used to combine the paths. Check if the models_dir exists. If it does not exist, create the directory using os.makedirs. Use the shell command, cp to copy the section pre-trained model files from the /input/chars pre-trained models/directory to the .chars/models/directory. The exclamation point character is used in IPython or Jupyter Notebook to run shell commands directly from the code cells. Use the shell command, ls to list the contents of the .chars/models/directory. This is to confirm that the section model files have been copied successfully. The purpose of this code is to set up the necessary directories and copy the pre-trained section model files for later use in the project. This is particularly useful when using shared environments like Kaggle or Google Colab, where pre-trained models might not be available by default. This code snippet defines several directory paths related to a dataset of fire and non-fire images, and sets up a list of categories for the classification task. Here's a step-by-step explanation. Define the base_folder variable, which refers to the root folder of the dataset, located at /input/fire dataset. Define the data_folder variable, which refers to the main data folder containing the fire and non-fire images, located at /input/fire dataset/fire_dataset. Define the train_data_folder variable, which refers to the folder containing the fire images, located at /input/fire dataset/fire_dataset/fire_images. Define the test_data_folder variable, which refers to the folder containing the non-fire images, located at /input/fire dataset/fire_dataset/non_fire_images. Create a list named categories, which contains two elements, fire_images and non_fire_images. These elements represent the two classes for the image classification task, fire images and non-fire images. Define the len_categories variable, which stores the length of the categories list, i.e., the number of classes in the classification task. In this case, the value will be 2. This code sets up the necessary directory paths and categories for a binary image classification task using a dataset of fire and non-fire images. The actual implementation of data loading, preprocessing, and model training is not present in this code snippet. You would need to add those parts to complete the project. This code snippet iterates through the fire and non-fire image folders, counts the number of images in each category, and creates a list called train_data containing information about each image. Here's a step-by-step explanation. Initialize an empty dictionary called image_count to store the number of images per category, and an empty list called train_data to store information about each image. Loop through the categories list using enumerate, which returns both the index, I, and the category name, category. The TQDM function wraps the loop to display a progress bar. Create a variable class_folder that represents the path to the current categories folder by joining data_folder and category using os.path.join. Assign the current category name to the variable label. In the image_count dictionary, create a new key with the category name and initialize it with an empty list. Loop through the image file paths in the current category folder using os.lister, os.path.join, class_folder. For each image file path, append the category name to the list in image_count category. This will result in counting the number of images per category. For each image file path, append a list to train_data containing the following elements. A string that represents the relative path to the image file, formatted as category/path. The index I, which corresponds to the category's numerical label, 04 fire_images, 14 non_fire_ images. The category name. After the loop, the image_count dictionary will store the number of images per category, and the train_data list will contain information about each image, including its relative path, numerical label, and category name. This data structure can be used for further processing, such as loading and pre-processing the images, splitting the data into training and validation sets, and training a machine learning model. This code snippet iterates through the image_count dictionary and prints the number of images for each category. Here's a step-by-step explanation. Loop through the key value pairs in the image_count dictionary using the .items method. The key variable represents the category name, example, fire_images or non_fire_ images, and the value variable represents the list of image file paths for that category. For each key value pair, print a formatted string showing the category name, key, and the number of images in that category. The len value expression calculates the number of image file paths in the value list. After running this code, you will see the number of images for each category, fire_images and non_fire_ images, printed in the format category-count. This information can help you analyze the distribution of images across categories and ensure that the dataset is balanced or identify the need for data augmentation or resampling techniques. This code snippet creates a pandas data frame from the train_data list, which contains information about each image, and then displays the shape in the first few rows of the data frame. Here's a step-by-step explanation. Create a new data frame df using the PD data frame function. Pass the train_data list as the data source and provide a list of column names, file, ID, label. File, the relative path to the image file, formatted as category/path. ID, the numerical label of the category, 04 fire_images, 14 non_fire_ images. Label, the category name, example, fire_images or non_fire_ images. Display the shape of the data frame df using the .shape attribute. This will show the number of rows and columns in the data frame, where each row corresponds to an image and the columns contain the file path, numerical label, and category name. Display the first few rows of the data frame using the .head method. This will give you an overview of the data structure, making it easier to understand the content and format of the data frame. The data frame created in this code snippet can be used for further processing, such as loading and pre-processing the images, splitting the data into training and validation sets, and training a machine learning model. This code snippet defines 4 image processing functions that perform masking, segmentation, sharpening, and image loading. Here's a detailed explanation of each function. Create underscore mask underscore for underscore plant image. This function creates a mask for an input image by thresholding the image in the HSV color space. Convert the input image from the BGR color space to the HSV color space using cv2.cvt color. Define the lower and upper bounds for the HSV threshold. The lower bound is 0, 0, 250, and the upper bound is 250, 255, 255. These bounds are used to filter out low-intensity pixels. Create a binary mask using cv2.inRange with the input image and the defined bounds. The mask will have white pixels where the image is within the bounds and black pixels otherwise. Define an elliptical structuring element, kernel, of size 11, 11, using cv2.getStructuringElement. Perform morphological closing on the mask using cv2.morphologyX with the defined kernel. This operation dilates the mask and then erodes it, helping to close small holes and connect nearby regions in the mask. Return the processed mask. Segment underscore image, image. This function segments an input image using the mask created by the create underscore mask underscore for underscore plant function. Obtain the mask for the input image by calling the create underscore mask underscore for underscore plant function. Apply the mask to the input image using cv2.bitwise underscore in. This operation retains the original pixel values where the mask is white and sets the pixel values to 0 where the mask is black. Normalize the output image by dividing it by 255, which scales the pixel values to the range 0, 1. Return the segmented image. Sharpen underscore image, image. This function sharpens an input image. Apply a Gaussian blur to the input image using cv2.GaussianBlur with a kernel size of 0, 0, and a standard deviation of 3. This produces a blurred version of the input image. Combine the input image and the blurred image using CV2.add weighted. The input image is weighted by 1.5, and the blurred image is weighted by -0.5. This operation enhances the edges and fine details in the input image. Return the sharpen image. Read_img, file path, size. This function loads an image from a file and resizes it. Load the image from the specified file path using image.load_img and resize it to the target size using the target_size parameter. Convert the loaded image to a number py array using img_to_array. Return the image array. These functions can be used in a preprocessing pipeline to load, resize, segment, and sharpen images before feeding them into a machine learning model for training or inference. This code snippet creates a grid of sample images randomly selected from the dataset using Matplotlib. Here's a step-by-step explanation. Set the number of rows, nb_rows, and columns, nb_cols, for the grid of sample images. In this case, the grid will have 3 rows and 5 columns. Create a figure, and axis, using plt.subplots with the specified number of rows and columns. The fig size parameter sets the width and height of the figure in inches, 10 inches wide, 5 inches tall. Set the title for the figure using plt.subtitle to sample images. Use 2 nested loops to iterate through the rows and columns of the grid. For each row I and column j, remove the x-axis and y-axis tick labels by setting them to empty lists with axs I j.zaxis.set_tick labels and axs I j.yaxis.set_tick labels. Randomly select an image index from the dataset by calling np.random.randint 1000. This assumes there are at least 1000 images in the dataset. You could replace 1000 with a dynamic value based on the dataset size, such as len, df. Read the image file corresponding to the randomly selected index using the read_img function, passing the file path from the file column in the data frame, df, file, index, and the target size, 255. The image is divided by 255 to normalize the pixel values to the range 0, 1. Display the image in the grid cell at row I and column J using AXSI.J.ImShow. Display the figure with the grid of sample images using plt.show. After running this code, a grid of 3 by 5 sample images will be displayed. The images are randomly selected from the dataset, allowing you to visually inspect the dataset and get an understanding of the types of images it contains. This is a useful technique for exploring and understanding the content of image datasets. This code snippet demonstrates the image processing pipeline on a single image from the dataset. It loads the image, applies the mask, segments the image, sharpens it, and then displays the results using Matplotlib. Here's a step-by-step explanation. Load an image from the dataset using the read_img function. The file path is taken from the file column in the data frame, df, file, 102, and the target size is set to 255. Create a mask for the loaded image using the create_mask_for_plant function. Segment the loaded image using the segment_image function. Sharpen the segmented image using the sharpen_image function. Create a 1 by 4 grid of subplots using plt.subplots. Set the figure size to 10, 5, and store the figure in axes and the fig and ax variables, respectively. Set the main title for the figure using plt.subtitle and adjust its position using the x and y parameters. Adjust the spacing between subplots using plt.title_layout. Set the title for each subplot using the axi.set_title method, where I is the index of the subplot, 0 to 3. Display the original image, mask, segmented image, and sharpened image in the subplots using the axi.imShow method. After running this code, a 1 by 4 grid of subplots will be displayed, showing the original image, mask, segmented image, and sharpened image. This visualization helps you understand the effects of each processing step on the image and allows you to evaluate the image processing pipeline before applying it to the entire dataset. This code snippet processes the images in the dataset and prepares them for input into inception model. The processing includes resizing, masking, segmentation, sharpening, and preprocessing specific to the inception model. Here's a step-by-step explanation. Set the input underscore size to 255. This will be the target width and height for resizing the images. Create a number py array x underscore train with the shape, number of images, input underscore size, number of columns in df, initialized with zeros. This array will store the processed images. Iterate over the file paths in the file column of the data frame df using enumerate and tqdm, which provides a progress bar. The index of the file path in the data frame is stored in the variable I, and the file path itself is stored in the variable file. For each file path, load the image using the read_img function, passing the file path and the target size, input_size. Apply the masking and segmentation to the loaded image using the segment_image function. Sharpen the segmented image using the sharpen_image function. Preprocess the sharpened image for the inception model using inception.preprocess_input. This function applies specific preprocessing steps required by the inception model, such as mean subtraction and scaling. The input to the function should be a 4D array, so np.expand_dims is used to add a new dimension to the 3D image array. Store the preprocessed image in the x_train array at index I. After running this code, the x_train array will contain the processed images that are ready to be fed into inception model for training or inference. This code snippet prints the shape and size of the x_train array, which stores the preprocessed images for training. x_train.shape, the shape of the x_train array is a tuple representing the dimensions of the array. In this case, it will have the form, number of images, input_size, number of columns in df. This tells you how many images are in the array and the dimensions of each image. x_train.size. The size of the x_train array is the total number of elements in the array. It is equal to the product of the dimensions of the array, i.e., the product of the values in the shape tuple. This value gives you an idea of the memory footprint of the array. By printing these two values, you get an understanding of the structure and memory requirements of the processed images stored in the x_train array. This information can be useful for determining the feasibility of training a model on your machine or for making adjustments to the preprocessing pipeline if necessary.
This code snippet splits the preprocessed images and their corresponding labels into training and validation sets. The steps are explained below. Extract the ID column from the data frame df and store it in the variable y. This column contains the class labels, integer IDs, corresponding to each image in the dataset. Use the train_test_split function from the sklearn.model_selection module to split the x_train array, containing the preprocessed images, and y array, containing the corresponding labels, into training and validation sets. The function takes the following parameters. x_train, the array of preprocessed images. Y, the array of corresponding labels. Test_size, the proportion of the dataset to include in the validation set. In this case, 20%, 0.2, of the dataset will be used for validation. Random_state, an integer seed value to ensure that the random sampling of the data is reproducible. This is helpful if you want to reproduce the exact same train validation split in the future. The train_test_split function returns 4 arrays, train underscore x, train underscore val, y underscore train, and y underscore val. These arrays represent the following. Train underscore x, the pre-processed images for the training set. Train underscore val, the pre-processed images for the validation set. Y underscore train, the labels for the training set. Y underscore val, the labels for the validation set. By splitting the dataset into training and validation sets, you can train a machine learning model on the training set and evaluate its performance on the validation set. This allows you to estimate the model's performance on unseen data and make adjustments to the model's architecture or hyperparameters as needed to improve its performance. This code snippet prints the number of fire images and non-fire images in the training dataset after splitting the data into training and validation sets. Y underscore train equals 0, dot shape, 0. This expression selects the labels in the Y underscore train array where the label is 0, fire images. The dot shape, 0, part of the expression returns the number of elements in this selection, which represents the number of fire images in the training dataset. The print function then displays this count with a descriptive message. Y underscore train equals 1, dot shape, 0. Similar to the previous expression, this one selects the labels in the Y underscore train array where the label is 1, non-fire images. The dot shape, 0, part of the expression returns the number of elements in this selection, which represents the number of non-fire images in the training dataset. The print function then displays this count with a descriptive message. By printing the counts of fire and non-fire images in the training dataset, you can gain insights into the class distribution of your dataset. This information can be helpful in understanding whether the dataset is balanced and if any adjustments or pre-processing steps, such as oversampling or undersampling, are needed to balance the classes for better model performance. This code snippet extracts features from the pre-processed images using the Deception model as a feature extractor. Here's a step-by-step explanation. Create Inception model instance with pre-trained ImageNet weights without the top classification layers and with global average pooling using the following parameters. Weights equals ImageNet. Load the pre-trained weights from the ImageNet dataset. Include underscore top equals false. Exclude the top fully connected layers, which are used for classification. This leaves the convolutional and pooling layers that can be used for feature extraction. Pooling equals average. Apply global average pooling to the output of the last convolutional layer, reducing its spatial dimensions to 1 by 1. This results in a fixed size output that can be fed into a classifier. Extract features from the training images, train underscore x, using the section model by calling its predict method with the following parameters. Train_x, the pre-processed images for the training set. Batch_size equals 32, process 32 images at a time for better computational efficiency. Verbose equals 1, display progress information while the features are being extracted. The extracted features are stored in the bf_train_x array. Similarly, extract features from the validation images, train_val, using the section model and store the features in the bf_train_val array. After running this code, you will have two arrays, bf_train_x and bf_train_val, containing the extracted features for the training and validation images, respectively. These features can be used as input to a classifier for training and evaluating the model's performance. This code snippet prints the shape and size of the feature arrays obtained after using the section model as a feature extractor for both the training and validation datasets. bf_train_x.shape. The shape of the bf_train_x array is a tuple representing the dimensions of the array. In this case, it will have the form, number of training images, number of extracted features. This tells you how many images are in the training set and the number of features extracted for each image. bf_train_x.size. The size of the bf_train_x array is the total number of elements in the array. It is equal to the product of the dimensions of the array, i.e., the product of the values in the shape tuple. This value gives you an idea of the memory footprint of the array. bf_train_val.shape. Similarly, the shape of the bf_train_val array represents the dimensions of the validation set in the form, number of validation images, number of extracted features. bf_train_val.size. The size of the bf_train_val array is the total number of elements in the array, which is equal to the product of the dimensions of the array. By printing these values, you can get an understanding of the structure and memory requirements of the extracted features for both the training and validation sets. This information can be helpful for determining the feasibility of training a classifier on your machine, or for making adjustments to the feature extraction process if necessary. This code snippet creates a simple feed-forward neural network using Keras Sequential API and compiles it for training. The steps are explained below. Instantiate a new sequential model. The sequential model is a linear stack of layers that you can easily create by passing a list of layer instances or by calling the add method on the model. Add a dense layer with 256 units and a rectified linear unit ReLU, activation function to the model. This is the first hidden layer of the neural network. The input_dim parameter is set to the number of extracted features from the section model, i.e., bf_train_x.shape 1. This ensures that the input shape of the first layer matches the shape of the extracted features. Add another dense layer with 64 units and a ReLU activation function. This is the second hidden layer of the neural network. Add a final dense layer with 1 unit and a sigmoid activation function. This is the output layer of the neural network, which will produce a single output value between 0 and 1 representing the probability of an image belonging to the FIRE class, class 0. Since this is a binary classification problem, the output layer has only 1 unit. Compile the model by specifying the optimizer, loss function, and evaluation metrics. Optimizer equals Atom. Use the Atom optimization algorithm for gradient descent during training. Loss equals binary_cross entropy. Use binary cross entropy as the loss function, which is suitable for binary classification problems. Metric SAT face accuracy. Use classification accuracy as the evaluation metric during training. Call the summary method on the model to display a summary of the model's architecture, including the number of parameters in each layer and the total number of parameters in the model. After creating and compiling this simple neural network, you can train it on the extracted features from the section model, bf_train_x, and evaluate its performance on the validation set, bf_train_val. This code snippet trains the neural network model created in the previous step on the extracted features using the fit method. Here's a detailed explanation of the code. bf_train_x. This is the array of extracted features from the training images using the section model. It serves as the input for the neural network model. y_train. This is the array of labels corresponding to the training images. It serves as the ground truth for the neural network model during training. Epochs equals 100, the number of times the entire dataset will be passed through the neural network during training. An epoch is one complete iteration through the training dataset. Here, the model will train for 100 epochs. Batch_size equals 32, the number of samples per gradient update during training. The model will be updated after processing 32 samples. This is a hyperparameter that can be tuned to balance computational efficiency and convergence speed. History, the fit method returns a history object, which contains a record of training loss values and metrics values at successive epochs. You can use this information to analyze the training process, plot learning curves, or determine the optimal number of epochs for training. The fit method trains the neural network model on the extracted features, bf_train_x, and corresponding labels, y_train, for 100 epochs with a batch size of 32. After training, you can evaluate the model's performance on the validation set, bf_train_val, and use the history object to analyze the training process. This code snippet creates a 1 by 2 subplot and plots the training loss and training accuracy over the course of the training process using the history object returned by the fit method. The steps are explained below. Fig x equals plt.subplots 1 2 fig size sadface 14.5. Create a 1 by 2 subplot with a figure size of 14.5 using the plt.subplots method. This creates a single figure with 2 subplots side by side. The x variable is a 1D array containing the 2 axis objects that correspond to the subplots. ax0.set_title, training loss, and ax1.set_title, training accuracy set the titles of the 2 subplots. The first subplot will display the training loss, and the second subplot will display the training accuracy. ax0.plot, history.history, loss, color equals salmon, lw equals 2 plot the training loss values stored in history.history, loss, on the first subplot, ax0. The plot's line color is set to salmon and the line width, lw, is set to 2. ax1.plot, history.history, accuracy, color equals green, lw equals 2 similarly, plot the training accuracy values stored in history.history, accuracy, on the second subplot, ax1. The plot's line color is set to green and the line width, lw, is set to 2. After running this code, you will see a visualization of the training loss and training accuracy over time epochs. This can help you understand how well the model is learning from the data, identify potential issues, such as overfitting or underfitting, and determine the optimal number of epochs for training.